Okay, good morning, everyone. My name's Sylvia Clark, and I'm from the Queensland Minerals and Energy Academy. And today we're going to be talking to Amy Lawrenson and Nathan Walpole from Glencore's Mount Isa Mines. What we'll do today is if you've got any questions for Nathan, if you could let your teacher know and she can put them in the chat for us, and then we'll be able to speak to those questions at the end. I know that we've got some year 10 students and some year 11 students, so we've had a little chat beforehand about what types of things the year 10s have been we'll look at in chemistry, and also what is in the beginning of the year 11 curriculum as well. So I'm going to hand over now to Amy, and she's going to briefly talk about Glencore's Mount Isa Mines. Thanks, Amy.
Thanks, Sylvia. Can you hear me okay? Coming
Yes,
through fine. Excellent. Well, it's really exciting to be here and be joined by up and coming chemistry students. We absolutely love hearing about students that are studying in this unique field, and I'm actually in the people development field, so thankfully we have wonderful people like Nathan, who is a metallurgist, and Nathan is actually a second-year metallurgist, but he's held a number of positions already, even with a short time at Glencore Mines. So he's already got such a wealth of experience, but I'm sure still learning every day. So I'm really excited to be able to introduce you to Nathan, who will be able to answer all your questions today. And then I'll hang around. Obviously, some of the subjects will get a bit over my head, and that's why you guys are on here with Nathan and Sylvia. But I'll come on at the end. So if you would like to ask any questions about what it means to have a career in the mines, or any kind of pathways we have, or what it means to be a graduate, or how can you try before you buy with some of our work experience programs, you just let me know, and I'll be here ready to answer any of your questions. But let's get to the exciting part. So I'm really, really happy to introduce you to Nathan Walpole, who's going to take you through what it means for anything related to chemicals works in his role as a metallurgist with Mount Isa Mines. Thanks, guys.
Alrighty. Nope. Oops. So I'm just going to share a presentation with everyone. All right. So this is a Zinc Processing Good Shepherd presentation, and what I'll do is I'll break it down into two components of the two operations that go on at Mount Isa Mines. We have the concentrator and we have the lead smelter. So I've had a lot more experience down at the lead smelter, working there for 18 months. And now I'm up at the concentrator working as a planning metallurgist. And what my role entails here is to basically ensure that all production and planning is going according to our schedule, and we troubleshoot any issues for the concentrator and for the smelter. So you're probably wondering, what is a metallurgist? Well, I actually didn't find out what a metallurgist was until my third year of university, when I was studying chemical engineering. But metallurgy, in essence, is the science and engineering of just metallic elements. It covers extractive metallurgy, so digging it up from the ground, processing it, converting it into a material product, and then finalize it into some form of alloy or some form of pure metal. What we're in charge of, we're just in charge of ensuring that the process is stable from start to finish. We focus on process and plant improvement, and we ensure that everything goes according to plan. Why metallurgy is important in industry? Well, most people don't understand that once you mine it from the ground, it actually takes a lot of energy to actually process it. And the reason why it takes a lot of energy is because you can't refine metals straight away. You actually have to concentrate it. If you refine it straight away, it actually takes a lot of energy, which means a lot of money, which means you don't make a lot of money. So it's this balance of economics and chemistry that kind of intertwines metallurgy. And it's very important because we convert rocks into materials which can be very useful, like batteries. So battery technology is one of those upcoming fields where metallurgy is playing a huge part in. So I'll start off with concentrator operations. So this is like concentrating a product from the ground. So this is just a general bird's eye view of the site. This is where you have your material from your mine essentially is crushed. It goes up into this heavy medium plant and just it's separated there, and it goes into your concentrator for processing. In your concentrator, into your sag mill, and then goes into the concentrator, and then goes into your thickener, where you then basically recover most of your water. Because what people don't realize is the second most important resource or mineral in mining or in mineral processing is actually water. So water is a very, very valuable product, and we need that very often. And this is where I work. So I work down here. So just to give you a simple overview of our flow chart, you have the mine, it crushes the material, it then goes into a sag mill. So this is material that's about 17 centimeters. That's then crushed down to a very fine size, about 2 centimeters. This then goes into another mill, essentially, which goes down even further to you get 100 micron, essentially. Now, for a rule of thumb, the human hair is about 35 micron, 35 to about 75 micron. So you want to get your mineral to the size of basically 2 human hairs. And the reason being is because it makes it easier for those physical chemical reactions to take place. And that's where you go into your flotation. That's where you get your separation going. And then you have further separation with your cleaning, and then you go into your thickeners where you recover your water. And I'll explain those just in a sec. So this is your sag mill. Like I said, rock comes in about 17 centimeters. You basically grind it down to 2 centimeters. And then you go into your rod mill and you grind it from about 2 centimeters into about 100 micron. So rod and ball mills. This is a ball mill, this is a rod mill, and they're basically like big washings with ball medias inside. So if you imagine like a shot put ball, that goes into your ball mill and it just grinds it all down. So flotation, this is basically the essence of concentrator metallurgy. This is where all the chemistry takes its play, and this is where you get to see those fun reactions take place. So to imagine flotation simply, I like to use the analogy of you've got a glass of milk, you've got a straw, and you've got a piece of dirt. And the aim of the game is trying to get that piece of dirt back up to the top. So if you blow into the straw, you create bubbles essentially in your milk. But you want to get that dirt out of the milk. So if you blow hard enough, that dirt, which is a fine size, should actually adhere to the bubble and should actually blow over and then go over the top. And that's in essence what flotation is. You're trying to separate your valuable metal, so in this case our zinc, by using chemical reactions, or a series of reagents, and then activating it with basically collector and frother, and then using air to separate it. So often you've got pre-flotation, you've got rougher flotation, scavenger, and cleaner flotation. And I'll explain those a bit more. So this is what your circuits look like, and this is what your concentrate, so your overflow looks like, the bubbles that have been collected with your metal on top. Now, if we look at it from a chemistry perspective, that M here is your metal, and these molecules around it are your collectors. So it kind of attaches to them. And like olive oil in water solution, you want to make it hydrophobic. You want to make this mixture non-miscible. So what that means is you don't want them to mix together. You want them to separate as quickly as possible. So adding this collector coats it. You then add frother to kind of like a bubble mixture, and you essentially have made that metal hydrophobic, which then is inclined to basically release or be removed from the mixture. Now you add things like naphthalene sulfonate to basically depress or disperse the molecules so they're not evenly tied together, and you add copper sulfate to just activate the zinc metals. What that does is basically pretend it's a copper metal. The reason being is because copper metals float far more readily than zinc metals. So it's kind of like the chemistry thinks, oh, that's a copper mineral. I'll float that because that's easier to float than zinc. So it's manipulating the reaction chemistry, so to say. And then when you want to go to your thickener, after you've recovered most of your valuable metal, you want to coagulate it together, and then you want to pull it down to make it a dense liquid. You want to recover as much water as possible. And to do that, you add a flocculant, which is an organic long-chained polymer. So very similar to like detergent. You've got, when you add your collector to your mineral, you've got a non-polar group, which makes it hydrophobic, but you've got this polar group, which attaches around to it. And I believe there was like a famous video circulating during the early days of COVID-19 where students would put a little bit of detergent on their finger and essentially put it into a mixture where there was dirt, and the dirt would just separate to the end. That's pretty much what you're doing. That metal is kind of dirt, but this time imagine it attaching to the dirt or to the metal and proposing it in a certain direction. And that's essentially what you want. So after you have covered your metal, you send it to the thickener, which then densifies your solution, your slurry, where your underflow is about 75% solids, so the other 25% is liquid. You then go to a filter plant, and then you recover most of your liquid, and then you filter it, and it comes out as concentrate. So to just give a perspective of what exactly we produce on a day-to-day basis or each year, we produce about 4 million tons of material, or we mill 4 million tons of material. We recover about 325,000 tons of zinc, 155,000 tons of lead, and 170,000 tons of silver. So what we rail to Townsville is about 650,000 tons, and every year what we feed is roughly the volume of the Melbourne cricket ground. So if you remember, if you ever been to the Boxing Day test match, or you've watched the cricket, basically we feed the entire volume of Australia's largest cricket pitch every single year. So this is more of my bread and butter. This is the smelter operations, and this is more of the chemistry that I get involved in. So with your lead smelter, you've got 4 major areas. You've got your feed preparation, where you've got the concentrate from the concentrator. You basically filter it, becomes a bit of a cake where there's high moisture associated with it, but that's okay. You need that to agglomerate the particles together. Then you've got your first reaction, your oxidation reaction. Then you've got your second reaction, you've got your reduction reaction, and then you got your semi-refining. So I'll just go through them quickly. So this is what your filter looks like. It's this drum filter where it sucks in all that moisture, but releases this cake. This then cake goes into the oxidation reaction, which is the sinter plant, where you supply oxygen plus a little bit of heat to get it going, and Angelina or lead sulfide, and it produces lead oxide plus SO2 gas. And it's an exothermic reaction, so it releases more heat. So really, only around this area is where you need to ignite it. So you ignite it, get it to about 600 degrees, and then it just self-contains. You need no more management whatsoever apart from your oxygen. Because with your chemistry, if you control one of your reactants, you basically control your overall reaction. Then at the end, once it goes off the tip end and gets crushed, we create this product called sinter, which is main reactant inside is lead oxide. So with your lead oxide, you feed it into the furnace, and what you create is lead metal on one side, so on this side, and you create slag on the other side. And slag is kind of like your impurities.
Sorry, Nathan.
Yep.
Do you mind just turning your pointer on, because we couldn't just see which side you pointed to? If you
I
think
how
it's
do
just the little hand button at the top.
I see. Can you guys see it now?
I'm not sure if they can. I can't, but they might be able to now. Yep.
I'll probably do it like that. Probably the best way to do it. So this is your lead, and this is your slag. So to just explain the reduction reaction, essentially, your reduction reaction is where you use carbon monoxide to create, plus lead oxide to create liquid lead. And what happens is it's kind of like imagine a chamber. In that chamber, you have certain layers or certain zones. In your top zone, you have your feed zone. That's where you add your feed material. In your second zone, you've got your reduction reaction. And that's where you have the lead oxide reacting with the carbon monoxide. Then in the middle zone, you have your fusion zone. That's where you have all the impurities in your lead oxide or in your sinter reacting to form slag. And then at the bottom, you have your reaction zone. So around here. And that reaction zone is basically the burning of carbon with oxygen to create CO2 plus heat, which then reacts with more carbon to create carbon monoxide. So that carbon monoxide flows up to the top, reacts with the lead oxide. That lead oxide is turned into lead droplets. That drips down like rain, goes down to the bottom, and then comes out into a forehearth, which then is separated on the layers of essentially density. Because lead is quite heavy, it settles down at the bottom, and slag is quite light, sets up on top. So like olive oil and water, and then you separate them based on the height of those densities or the volumes in which those mixtures take place. Then what you do is you do some semi-refining, you upgrade it, and this adds a little bit of caustic, so sodium hydroxide, and then you create lead blocks from this product. And this is about 99.7% lead. This is then labelled and is transported to BRM, so British Refined Metals, in London. So we produce about 120,000 tonne of it each year, and normally we treat about 245,000 tonne of ISO concentrate. So yeah, that's in essence the presentation.
That was amazing. I have learnt, honestly, so much. And I'm sure that the students are thinking the same. So I guess while they're thinking of all the questions that they would like to ask, I've got a few. So I guess the first thing that I was wondering is, what was the pathway that you took to become a metallurgist? So sort of like, what subjects did you do at school? Did you do at uni? That type of thing.
Yep. So when I started off in year 11, I had no idea what I wanted to do. What I did know is that I really liked maths and I really liked science. So I did your basic maths, I did your chemistry, and I did physics as well. And I really enjoyed those subjects. What I noticed is after I completed my year 12 studies, I didn't know what I wanted to do, but what I did know is I still like those subjects and I wanted to do more of those. So I thought about different types of engineering. I thought about chemical engineering, and through my chemical engineering degree, I learned to have I learned an appreciation for the different fields. And one of the fields that we learned about was metallurgy. And then just so happened it aligned with my interests. And then I happened to get my dream job at the smelter, where I get to see reactions take place.
Yeah, cool. So I guess you've also kind of answered why you decided to become a metallurgist. So it was really that kind of ongoing enjoyment, I suppose, of those subjects. It kind of led you to where you were meant to be in a way, I suppose.
Yeah, exactly. Yeah.
Yeah. Okay. So, well, then, what's your favorite part of your job?
My favorite part is definitely going outside and doing my inspections. There's something satisfying about just having a look at the plant and seeing a reaction take place, or seeing going at the start of the plant, so at the feed section, walking the entire way through to the end where you see lead bullion. That's my favorite part. Or from the concentrator, seeing something fine crushed to about 20 centimeters, so as big as your hand, to become this liquid solution. It's just fascinating to see within a space of time, you've seen this entire process change.
Yeah, that I can imagine that would be quite satisfying, quite rewarding, really, to see, like, to be able to witness that whole process. So I get that. That sounds pretty good.
Yep.
So you did speak a lot about the different types of reactions that take place within the operations. Um, I was just wondering, so I know that the year 11s, so I know that the year 10s will have been probably looking at, or if they are in their chemistry unit, different types of reactions and like how the reactions are used, for extraction and that type of thing. And I think that you've touched on that quite well. And I think also be important to the year 11s. I know that they also though would be looking at different types of analytical techniques, and I was wondering if you could touch on what types of maybe analytical techniques that you use in your role or are used within the operations at Glencore.
So one of the big analytical techniques employed at Mount Isa Mines is essentially XRF. So what I like to distinguish them into two groups. You have your chemist, and then you have your metallurgist. The metallurgist is the one who likes to look at the big picture, likes to see how everything is intertwined, while the chemist likes to look at the intricacies of certain problems and certain issues. So when with our daily sampling, for instances, we give that to the chemist. The chemist performs their XRF testing, which involves looking at the composition of each stream. Mm-hmm. What that does is that provides certain information about that stream, which then correlates to the metallurgist, and they can align that information and match it up with what they're currently seeing in the plant. And more often than not, if you're able to see an anomaly occurring in one section of the plant, it's more likely going to appear in another section. And that matching up is what makes it so fascinating as a metallurgist. You see the bigger picture. While a chemist just is able to pinpoint what is exactly wrong in that stream. And that's where the two fields cross over, essentially. So, yeah, so in summary, one of the big techniques employed at this mine site is XRF, which is an analytical tool for identifying stream composition.
Yeah, that sounds really, really cool. So I guess it does really showcase how much of a team kind of effort it is to make sure that everything's working the way it should be. So we've got a question from one of the students. They're wondering how efficient is the refining process and what affects this?
So the refining process involves the addition of caustic. So off the top of my head, it's sodium oxide reacting with your liquid lead, which is removing arsenic and aligned with it. So you create this arsenic complex, which impacts your processes or impacts the purity of your product. So then that creates a solid material which is then scooped out. So when I was doing my metal balance, in November, don't quote me on this, but off the top of my head, it was about 97%. So from that information, we were very good at refining, but we were too good. So in other words, we were putting too much energy into refining the process with not receiving the same economic benefit that we should have seen if we performed to a lesser extent. So that essentially aligns with the economics of metallurgy as well, which is something that I often did not understand as a student throughout university, but it's something you learn more as you progress through your field.
Sounds like you never have a boring day, Nathan. Sounds full on every day. And that was a great question too from the students.
Yeah, definitely. So I guess with Nathan, just on that,
Yep.
kind of learning about the economics side of things through your roles that you've undertaken, I guess your interest in maths then would have been quite beneficial to that. Would you agree?
Oh, absolutely.
Yeah.
And that's where what I like is, and this is the big thing. Like when you go from high school to university, they really complicate things, and you've probably got older brothers or family members or even friends that have joked about how difficult engineering maths is. But when you go back into the field, it's the core units or the core knowledge from year 10, year 11, and year 12 that plays a bigger part, because you're working with people who haven't studied engineering. You're working with people who have done marketing or who've worked in hygiene or in health and safety, and you've got to come together as a team. But you can't use complex engineering maths. No one's going to understand that. Yeah. So you break it down to the basics, and that's what I find rewarding. You're seeing that as I've gotten older, school has often been the most important aspect of any education.
Yeah, wow. Hope you've all listened very carefully to that point that Nathan's made. Now, we've got another question here as well from one of the students. They've asked, how is your area responding to the green energy push from the community as a whole?
That's a very good question. So what we're doing now is we're implementing new procedures and new protocols, and this has come down from the general manager through our health and safety environmental department, and to ensure that we're minimizing our emissions and ensuring that we are adhering to the government legislation and standards. Now, Glencore has always prided itself on being ahead of the curve. So often we have monthly reports where we see how we've been performing, and we relate it to our benchmark and to the government benchmark. And more often than not, if we're not adhering to our Glencore benchmark, there's often a massive investigation into why, and procedures put in place to ensure that we are responding to it appropriately. So in summary, it's a big push in our organisation, and it's something that will continue to future's end. And just over these past few months, just from the changes of COVID-19 and seeing how all of Australia has reacted to this situation, there's been a big mental state, the state in terms of understanding our current issues has completely been thrown in a new light. So we're now trying to adhere or adopt new policies and procedures that will ensure that we are able to make this place as sustainable as possible.
That's really good. I don't know if you can answer this question, but how do the like Glencore's guidelines differ from the government's guidelines?
So the big one that I look at is in terms of our lead safety and all that.
Mm-hmm.
So we always like to have our levels a lot lower because we ensure that we're looking after the safety of our operators. So we want to make sure that everyone is come to work safe and healthy and goes home in the same state. So if we see something that is borderline to that is not acceptable to our levels, we intervene and put in relevant safety management procedures and so forth. And likewise with our hygiene, we do that the same thing with certain emissions as well. So that's something that we want to make sure that is in place and can effectively take things to a new light, essentially.
Yeah, that's really good. I thought it was worth asking because it's a very interesting space to be in, and I know that the students now, you know, it's the work environment that they go into in, you know, 6-8 years time is going to be very different to what it looks like now and as it looked, you know, 6 or 8 years ago. So you know, it's definitely an interesting space to be in for sure. So I guess I had another question. This is a bit more about your like kind of your lifestyle. So I was just wondering, what are you working on a roster? Are you flying in, flying out, or do you know, that type of thing? And what sort of hours are you working in your normal kind of work day, I suppose?
So it depending on the role, it can change or it can vary. So when I was doing my plant metallurgy work, I was working 8 days on with 6 days off, and they were 12 to 13 hour days. So very long days, but you've got to keep in mind when you're at a plant, it's a 24-hour operation. There's no sleep for the wicked, essentially. You've got to keep going. So when you get your week off, it's fantastic because you have that long period of time to recover. But sometimes firefighting can get a bit exhausting and a bit overwhelming, and you don't get to focus on projects so much. So when you change roles into, let's say, a more office-based role or project-based role, you move to more of a typical 9 to 5, 4 days on, 3 days off, 5 days on, 2 days off roster, where basically you're working over a long period of time to implement projects, but in a matter that doesn't necessarily tire you out. So the rosters are set up to ensure that you're basically fit and healthy and working as effectively as possible. Now, you probably may say a week on and a week off is fantastic, but when you miss every weekend and all the good events like rodeos last year were on the weekends you're working, it gets a bit upsetting. So when you go into this role, it becomes a bit more exciting.
And,
Yes.
and you get to do so many rotations too. Hey Nathan, so already you've gone to a few different places and you've got more places that you'll still go to, so you've got opportunities to learn from lots of different fields that you come in contact with on a daily basis. Hey.
No, absolutely, and everyone is so friendly. And the one thing I've noticed is they want to share you their job or the information about their job, which means that you're always learning about what they're learning, which helps you as a person and also helps you in your work, which I find is very rewarding.
Yeah, that's a very good point. So we're coming to the end now of our webinar today. I guess my closing question for you, Nathan, would be, what is the one thing that you would like people to know about metallurgy or being a metallurgist?
Okay, so this was something I've been thinking about a lot. And the only thing I can say is, and this only made sense to me when I guess I was working as a metallurgist, if it can't be grown, it's got to be mined. So you think about everything in the world, and you think about everything that can be grown from agricultural perspectives, but then you think about things like batteries, cars, even toothpaste. Like, you need to mine those materials to make those products, and that's what I find pretty interesting. It's we take for granted that a lot of our products or a lot of things that we enjoy in life, like this laptop that I'm using to speak to you guys, is actually mined from materials, and I find that to be quite fascinating.
That's definitely a very good point, and I think that to be able to have that in your mind, it really does change the way you see the world for sure. So thank you. Just before we finish up, there was just a couple of things that I wanted to quickly show. So
Yep.
part of what the Queensland Minerals and Energy Academy has, there's a website called Awesome Resources. Now on this website, there's lots of different activities and interactives and that type of thing. But I thought what I would call out today is that there's a selection of videos of people talking about the resources, their career in the resources sector. So they're really good for our students maybe to check, see, what other roles are like as well. You've heard from a metallurgist today, and there's some other roles on there as well. And also just a little bit, those few things about QMEA. So we've got a website, a Facebook page, and an Instagram that you can definitely check out. So thank you all so much for participating today. Thank you to the students for your questions and your attention. If you have questions, coming out of this, please share them with us, and we can definitely get in touch with Nathan to see, for him to answer those. Thank you so much, Nathan and Amy, for joining us today. I know,
Sure.
it's hard sometimes to find the time in your busy schedule, but we are very, very appreciative, both from a Queensland Minerals and Energy Academy perspective, but also from the school's perspective as well. So thank you all. Thank you all for your time today.
No problem. And just one sneaky comment, if I may, Sylvia, and to everyone that's watching today. Last year when we did work experience, we only had one person that put their hand up to say that they're interested in chemical engineering. Now, from listening to Nathan speak so passionately today, I can tell you right now, if I was back at high school in your position and work experience came up, seeing how he explained everything and was so friendly, it was so easy to listen to, I'd absolutely love for when the next work experience comes around, if anyone watching today puts their hands up, and we'll be able to pair you up with Nathan and all of his amazing colleagues. We saw some walking past today, but you'll be able to see firsthand for yourself what it really means to be a chemical engineer, what it means to do metallurgy. So you can see, I'm sure Nathan will be more than happy to host you. So please, 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 all you wonderful people who are watching today, do sign up for work experience so you can come and join Nathan and maybe go and see all the exciting and fun things that he does on the daily. So thanks very much.
Thank you, everyone. Thanks.
Thank you.
Thank you. I'm just going to stop the recording.